Now, now I know why marketing kept asking for pictures of us.
I was totally Chewbacca, by the way, between that duo.
The funny thing is, like, do you remember this picture?
I do not. Is it real?
Well, so what I notice about it is that guy seems shorter, and he seems a little fatter than you. I wonder who it actually is.
Oh.
It is actually hard for us to find photos together. I don't actually know why, but I do know of one because I found one the other day. I sent it. I don't know why they didn't use it. I thought it was great, so I made them put it in. How many people here like karaoke? Now, it's okay if you like just watching it. That's also part of the fun. So, I don't know, Alon, maybe you could tell us a little bit about what we see in this picture.
So, in the Israeli office, we have a jam session like almost every month. And anyone can join, anyone can sing, anyone can play. And it's a great experience. And you know you're surrounded with good people that love each other because even though you're a bad singer, people continue having fun, clapping their hands and singing along. So it's just a great experience. And anytime our teams across the globe come in, we throw out a party for them. So it's a great fun.
It is a lot of fun. So if you're ever in Israel, visiting VAST or for other reasons.
This is open for customers too, by the way.
Come on down. We won't judge. You can judge us. That's okay. I'm going to hand it over to Alon because he's actually got some interesting things to say.
Okay. Thank you, Andy. Thanks, everyone, for coming out. We're very excited to have you. Almost emotional to see, all those customers here at the same place at the same time. Almost feels like our wedding. And in this session, we want to make it real. We want to show you how the VAST AI operating system is being put into use. And we'll take an example mission of building robots to go through the different phases of AI development. We're going to start with model training, then we'll go to agent building, and eventually we'll talk about fine-tuning to create a continuously improving system. So let's start with training. Our reference to the transformers is not about the movie. It's an LLM architecture. It's also because we don't want to pay royalties. It was published in 2017 by 8 Googlers in a seminal paper called Attention is All You Need. Initially, they used it for translation, but then they quickly realized it can be generalized to what we know today as LLMs. So what is an LLM? It's a mathematical equation, a huge one with up to 1 trillion parameters, even more. As an input, it gets a prompt. Those are the words, the questions that we give to those models. The weights are the majority of those parameters. They get tuned and set with the right values throughout the training process. And then we have outputs, which are called tokens, and they're actually words that we get back. The training process starts by taking a large data set, a ton of examples. It's examples of prompts and expected responses, and the training process iteratively tunes the values of those weights to get the model to spit out the best results. Now, this is a very long process, very compute-intensive, but the nice thing about it is that it's scalable. It can span tens to tens of thousands of GPUs to reduce the training time, which can still take months for very large models. Now, for physical AI use cases, like building robots, we need models that can understand the world, understand their environment. And this is where VLMs, or visual language models, come in. They can generate a description of what's happening in an image, or a video, or an audio clip. Their architecture is similar to LLMs, but instead of training on text samples, they train on images and videos that have captions or text descriptions saying what's in them. Now, we've seen this transition with our customers going from text to multimodal, go from petabytes to exabytes in less than a year. Now, let's see how training looks like from the VAST Data Store perspective. Customers use the VAST Data Store for storing home directories, data sets, and checkpoints. So what are checkpoints? Checkpoints are useful to avoid losing progress in case a job fails. The larger the model is, more GPUs get involved, and more time is needed to get the training done. There's higher likelihood of something bad happening. So here's an example of a training run of a very large model running on VAST. And you can see checkpoints land on the system every 15 minutes. There's a spike where the model gets stored on VAST. Then there's also a read spike somewhere towards the end where the job actually failed for some hardware-related reason, but quickly the model has been reloaded with one less GPU, read from VAST, and training continues. Now, a big question that customers ask is how much performance they actually need for something like checkpointing. So up until a couple of years ago, checkpoints were synchronous, meaning a GPU would go idle while writing a checkpoint. And this resulted in a painful trade-off where you had to build massive storage clusters to minimize checkpointing time. It was basically a race between storage and the GPUs. Today, checkpoints are asynchronous, meaning copying the checkpoint to a data store no longer blocks the training job at all. There's a short synchronous part where the job pauses and copies the model from GPU memory to CPU memory, staying on the same machine. And then training continues, and there's a background process moving that to the VAST data store. So back to the sizing challenge. Checkpoints are no longer the determining factor in sizing those clusters. Organizations are now facing a mix of different workloads that they do need to consider beyond just checkpoints. So let me give you just a few examples. Training also needs data preparation. Training needs large data sets, streaming video. Inference needs loading models. It needs KV cache, and it needs databases to perform search and to store conversations and memories. Now, one of the challenges organizations face is around the density of those AI factories. GPUs are now architected in rack-scale appliances. Power and cost involved drives organizations to need to build one shared piece of infrastructure and fold in all the different departments and teams and workload to drive up that efficiency. That means every AI factory is practically a multi-tenant environment. And at VAST, we applied the same principles to the data services. It's a single pool of hardware that should be leveraged across workloads, protocols, and tenants. One tenant could be running Kubernetes. Another could be training using Slurm. A third one could be doing data preparation using Spark. But then the challenge with multi-tenancy is the requirement for isolation. Isolation happens in several aspects. Resource isolation, using QoS for performance, using quotas for capacity to prevent noisy neighbors. Data isolation is about using different encryption keys for different users, different projects, different tenants. And administrative isolation that enables and delegates users the ability to be independent, to create all of those different concepts or constructs within the system, file systems, objects, buckets, events. Now, after the AI factory is up and running, there's now a new challenge. You have a zoo of users, workloads, machines, data. You then need observability to actually understand what's going on. And for us, observability is a core principle. We'd like the platform to be able to answer almost any question that would come from an infrastructure user, from an end user, even from an application. Andy, can you show us real examples of observability with VAST?
Well, I can. Actually, first off, who in this room participated in any hands-on labs today, or yesterday, sorry? Awesome. Now, I know they did fill up, and many of them were oversold, and well, it's good news for us, but it also means that not all of you got to participate. So one of the things I wanted to mention is that we're going to package these up in such a way that we can offer them again and again. We can either do it on your clusters, or we can provision systems in our lab and give you access to them. So if you missed out on hands-on labs, don't worry, we have you covered. A lot of what I'm going to show you today was covered in the labs that already existed. One thing I will say, this isn't going to be one of those demos where I show you all of the future things we're building. I'm more of a realist, and so everything you can do today, everything I'm going to show today, you can do today. Now, it does require 5.4 code, but we are moving many customers to 5.4 as it gains more traction, and we're getting a lot of good feedback from it. The first thing I want to show for observability is basically the main dashboard. Now, when I first started here, this dashboard looks slightly different. Those speed gauges are much bigger. We like F1 racing, Formula 1. We also like speed gauges. But to be honest, this isn't where you're going to focus your time when you actually have to understand what's happening in your system. So we added a lot more analytics. And Again, a lot of this is repeats for you who use it on a day-to-day basis, but I just want to mention that these UI enhancements to give you the ability to zoom in to a user or a specific host or a specific export or bucket, these came out of discussions with customers. In fact, I was talking with Eric at Pixar yesterday. They were one of the inspirations for why we have this. And so if you're a customer and you want to have something in the product, this is where you get it from. And actually, I didn't mention earlier, but Alon's the first employee at VAST. So if it's in the product, he probably had something to do with it. The challenge, though, when you're looking at observability isn't just that you want to know who's doing what, but you might want to know more granularity. So one of the things that we introduced in, I think in 5.3, now that I try to remember back in time, is the ability to audit data on the file system, but not just expose it using logs that people are used to. Most systems that expose audit logs push them into files, and those files need to be processed, parsed. Typically, people are using Elasticsearch or Splunk or some other pipeline to get it to a place that's searchable, which usually means it doesn't happen right away. It also means you have to maintain a separate system. So instead of doing that, we built in a way to query it directly using the VAST database. So the VAST database underpins so many things now. We're using it for all of these different use cases. The first one was the catalog, which I'll show you in a moment. But the audit log is interesting because you can use our SDK, but you can also use SQL. And so when I think about SQL, I think actually about how lazy I am at writing SQL. And so typically what I'll do is I'll pop open Cursor or some other tool. Actually, who uses AI coding assistants to write SQL? So if you don't, it's OK. But you can ask it obvious questions, and you can get pretty good results. So I one-shotted this. I made a couple adjustments to change like a path name or two because I had to change it from my system. But this query works, and I'm going to explain why I'm even showing this to you. Don't try and read that. I'm not a DBA. You're probably not a DBA. You're not going to understand what it's saying. But the point is, if I ask a question like, show me who's been writing to these directories over the course of the last day, or show me the top directories by I/O over the last day, how easy would that be to do on another system? It wouldn't be. And so if I just paste it in, it didn't do anything, did it? One moment, please. You got to love it when things don't exactly work. What's that?
Is it the 1 hour thing?
It's probably the 1 hour thing.
Let's debug it.
I'm gonna make it 4 hours instead. There we go. Look at that. So I won't explain everything here, but what I will say, this happens in seconds, right? Like I can see it with fine-grained ability the exact amount of I/O done to each directory, sorted in a way that gives an administrator or an ops person the ability to know who is trashing my system right now, who is doing the most work, what directories are growing the most quickly, and who's responsible for it. Like, these are questions you can answer easily. And so as we kind of go through the next steps of observation, you think about audit as a way not just to know who did what, but also who's doing what. And actually, if I want to think about something else, so one thing I'll mention is that I don't make slides. I can put this stuff on a screen, but if I put a slide on the screen, it's going to look like garbage. But of course, we had presentations this week. I co-presented with Pixar yesterday, and we needed slides for it. And so I wrote some slides. And then what I found was I uploaded my slide deck, and then the next day I looked for it, and it was gone. Now, so first I said, OK, well, what happened to my slides? Let me go and see if I can see what happened. OK, no one deleted it, so it must be somewhere else. So maybe they've moved it. Now, if anybody knows Jeff Denworth, our co-founder, he is adamant about not using AI for slides. I used AI for slides. And so he decided to change the name of my slide deck. This is the kind of thing I can answer very quickly. Now, obviously, you're not going to do this kind of a query. But again, auditing can be used for forensics. It can also be used for understanding telemetry in a much different way than most people are used to. The last thing I'm going to mention, and oh, by the way, most of you guys don't like looking at those things. So, I like pictures too, by the way. I don't know how to make them, but I like to look at them. And so this is an example of an easy-to-build dashboard on top of our audit database that can have dashboards like this built in seconds that show you a lot very quickly. And so if you want to understand the breakdown of how your I/O flows into the system, if you want to see which extension is writing the most data, if you want to make sure that you're not getting errors, in this case I see some errors for stale entries. So these are things you can find out right away across the entire system. It's very, very simple. And again, all of this stuff works right now. You don't have to go wait 6 months. You don't have to wait for Jeff to promise you something. You can do it right now. The last thing I'll mention is that we introduced something called the VNFS collector. And I forgot to put the GitHub on here, but Pixar, TAC, and several other of our customers who use us in large distributed ways needed to have a problem solved, which was, I need to know which jobs are doing the most I/O. It's very difficult for a file server to know what job is doing the I/O. So what we did is one of the guys on the team, Sagi, he created what's called the VNFS collector, which basically installs in the client a very tiny eBPF filter program that can capture the statistics for every NFS mount point and push them to Prometheus or to a VAST database table. In fact, if I want, I can look at a VAST database table by going to this client metrics section. I can look by host name, but really what I care about are job IDs. So now I can see the I/O done by job ID directly in the UI. Now, many people look at this as a way to see what's happening, but we're also extending it in the next release to also allow for the ability to quality of service based on job, which is pretty massive when you think about when you have thousands of jobs running, some of them are going to be more important than another. The big, long training job that can't fail, that's pretty important. So I think the last thing that I'll cover off on is all of the dashboards that I'm showing are things that you can pull. All of the features that I'm showing are things that you can use. But enough about observability. Let's turn it back over to you.
OK, so now that we solved for observability, what's the next challenge in building an AI factory? So what's more complicated than building an AI factory? That's right, building two. When customers grow beyond the power limits of a single data center, they go to 2 or 3, 4, and then they have a data management mess. Right? How do you synchronize information? How do you make sure information does not go stale? How do you protect information as you want it reachable across multiple sites? This is where data space comes in. And data space is a suite of features. It allows customers to protect their data by creating multiple copies. It also allows them to access their data without creating multiple copies using the global namespace. So we cover training and AI factories. The nice thing about it is you're likely not going to need to train your own model. There is a great ecosystem out there of commercial models and open source models. So let's talk about how models are getting put into use. This is where agents come in. So what is an agent? An agent, if you think about an LLM as a brain, an agent is a person. It has a goal. It has hands and legs as tools, eyes and mouth. And if you ask your favorite coding agent to write yourself an agent to do something, you're likely going to see something like this, like a constant loop, getting a goal, talking to tools, searching online, doing actions, until that goal is achieved. But when you need to think about deploying this agent and running this software, eventually it is a piece of software. How do you secure it? How do you deploy it? How do you handle failures? And then imagine scaling that up to 1,000 agents, right? Bringing it to production becomes extremely, extremely hard. So we wanted to start there. We wanted to start with the environment of where the agent is running, the runtime. Last quarter, we released the data engine with version 5.4. Now, it introduces simple but very strong primitives that enable building ingestion pipelines, agentic workflows, and many other types of workflows. A user starts by creating a pipeline, which is a graph connecting triggers and functions using events. Triggers fire based on a schedule or based on data changing on the system, like a video clip being uploaded, like a message arriving from a user. Functions are uploaded by users, or today, agents like Cursor. That's, by the way, also training on VAST. And events are really the blood vessels of the platform, enabling communication across those triggers, functions, or agents, and auditing at the same time because those events are persistent. So you can always observe and understand what those agents are doing. Now, I want you to envision an agent as a function. It runs in real time when a trigger fires. It's not wasting CPU or GPU constantly trying to do the same thing over and over again, just anticipating a change sometimes into the future. Now, the most elegant trait of this entire programming model is its scalability. You can go from 1 GPU to 10,000 GPUs, or 1 agent to 10,000 agents, not a single line of code changes. We can just scale it horizontally across a pool of compute. So we have a runtime. What else agents need? So let's start with the observability that we already mentioned. Our SDK allows users to emit traces and logs to actually see what the agent is doing, how it's progressing. Those can be also used after the fact for fine-tuning. As we learn from experience, we can actually improve models. Identity is a critical component to ensure an agent can only access what it should and nothing else. An LLM serving this agent needs KV cache. KV cache is that state of a session sitting in GPU memory. And when an agent goes idle, a modern inference engine like Dynamo would basically offload that session to storage, releasing the GPU memory. Jensen gave a nice analog yesterday of a person waking up in the morning, needing to take an hour to actually remember and recalculate, hey, what have I been doing over the past week and even who I am? So once an agent wakes up, sends a new prompt, Dynamo would actually reload the KV cache from storage extremely fast and provide that low latency effect that we want agents to have. Now, on the left-hand side, we see a bunch of tools. An LLM's knowledge is limited to the data set that it was trained on. So search tools are very popular, searching the web, searching a data store, searching a database. And that's very useful even for use cases like, my own personal robot will need to search its memories for where it put my favorite shirt if I can't find it. So let's talk about how agents actually search. This is where RAG comes in. RAG stands for Retrieval Augmented Generation. It's a common pattern, and it's based on ingesting files or objects into the VAST data store. The data agent then fires a trigger, invoking a function, doing ingest. Now, we do not hard-code those functions into the product, because customers can customize them, they can bring their own models, and they can bring their own customization to their own types of documents. Such a function would actually index the file into the VAST database. And now that the information is indexed, let's look at the agent's perspective. The agent would use a search phrase to find relevant information, and will use that result to update the context towards its goal. Now, what's nice about RAG is that it fixes a lot of the issues that models have. It enables access to fresh data, an unlimited amount of it. It also allows you to have citations and references to the source information, which is very important in fields like legal or medical, where there's no room for hallucinations or errors. So what's relevant? How do we determine what's relevant information? So this is a process called semantic search. Let's see how semantic search works. We start by generating a vector embedding from a search phrase. A vector is just a list of numbers that basically carry a semantic meaning of what's in this object, text, image, or a video. An embedding model is actually quite similar to an LLM. The first thing an LLM does is translating our words to vector embeddings. Now that you have a vector, the next step is finding the nearest vectors from all those objects that we've ingested so far into the system. But how do we measure distance and how similar those vectors are? The answer is a function called cosine similarity. So just imagine a vector as an arrow pointing to a specific direction. Arrows that point to the same general direction carry similar meaning. Now, comparing every two vectors doesn't scale to millions and especially not billions of vectors. And this is where vector indices come in. What we've done with the VAST database is introduce a new type of data structure and algorithm that enables low latency and high scale to trillions of vectors to keep the index fresh and consistent. So now that we described all the building blocks of an agentic application, let's look at a real one. Now, this is an example application Andy's going to show you, depicting taking real-time video from camera feeds, indexing them into the database, and enabling search through a nice UI, very simple one, generated by Cursor, and everything is available on our GitHub. Go ahead, Andy.
Awesome. So, the first thing I'll say, I mentioned that everything we show today is something you can do. So if you want, snap a picture, go to that site. It's our GitHub repository that contains all of the code that's going to be sitting behind what I'm doing today. It's not the same thing that was built during the DataEngine lab session over yesterday and today, because those are focused on sort of getting you go over the basics. Once you get over the basics, you can start to do more things. So let's kind of talk through a little bit about what the DataEngine is. First question, who in here has gone to this part of the UI? Oh, yeah. Some people. And those that didn't, it's probably because this is new. In 5.4, we introduced a new experience for users that isn't the typical administrative interface. There's now an application developer interface where you can go and create and develop pipelines that are derived from the functions that Alon was explaining. There's not a whole lot to it. What I'll do is I'll show you an existing pipeline that's going to be doing the video search and summarization one. I'll go to a visual builder, but for those of you that scoff at visual aids, you can always go and write your own YAML file by hand. But basically, I might zoom out just a little bit because it's a little bit too much. There's two different sets of triggers in this pipeline. The first one on the left basically says, whenever a video lands in this bucket, do something. And what is that something? Well, the next thing down below it is this VSS segmenter function. What this function does is it splits the videos into pieces. Why pieces? Because you can't take a 2-hour-long video and just create a quick summary on it. You need segments. And honestly, if you're trying to search for things, you would rather find the thing you're looking for and not find the gigantic thing that might have what you're looking for in the middle somewhere. So the first thing is we split it into segments. Typically, good segment sizes are between 5 and 15 seconds. It really depends on how much action is occurring and how much detail there is. What happens after that is those segments get pushed into another bucket, which then generates this next trigger to fire. The next trigger sends it through a series of steps. Now, one thing I'll mention, and I won't explain all of these steps, but you see how there's a line drawn between these different functions? Well, the importance of that is that the way that the VAST DataEngine operates is that we use our own internal message bus, our event broker that Jeff talked about yesterday, to be able to pass messages between applications. In those messages, we can pass context. So the output of the first function can become the input for the next. It makes it very easy to daisy chain these things together to concoct your own pipelines. You can mix and match, and we're going to start publishing more and more example reference functions and pipelines to our GitHub so you can get started without having to write any code. Now, the point of this is to take videos, split them into pieces, generate summaries, so basically sending the segments of video to a vision language model and asking it to generate a summary. That summary is text. It gets inserted into a VAST database table as a column, and then the text is then embedded by an embedding model, which of course generates numbers, as Alon was mentioning earlier. Those embeddings are also inserted into the same VAST database table in another special vector column so that it can participate in similarity and cosine search. The whole point of this is to have a searchable archive of video. Now, what can we do with that? Well, earlier Alon was talking about agents, and if you think about agents, what they need is some instruction. So I can go and search for video, but to be honest, the first thing you have to do is, let's imagine that you're training an intern to go and watch a bunch of old videos and tell you what they see. If you don't give them very specific instructions on what to look for, they're not going to look for what you care about. So you have to give it very specific details. So when you're ingesting footage of different types, it often makes sense to give the agent specific instructions on what you want it to look for. This also helps later on when you're trying to identify things that happened, events, alarms, let's say a fire, something caught fire. There's several different profiles, and these are just examples that we've created as we feed video into this pipeline. You can create your own. Everything on the left here is the entire GitHub repository for it. All of this code is downloadable. You can look at it yourself. Now, let's go to the actual interface that Alon was mentioning. If I come into this, I can search for things. I can obviously filter and identify the different sort of aspects that I want. One of the things that we think about when we think about training robots to do things is that you oftentimes have to give the robots examples on how to do it. If you just say, go make me some eggs, but you don't show it how to do it, how is it going to know? It's going to break them in the wrong place. It's going to throw them across the room, probably hit somebody with them. How do I make eggs? So I actually don't know what's going to happen right now. If you know me, you know I only do live demos. I don't know how to do recorded ones. So we searched in our vector database, and we came up with some results. OK, we got eggs, but maybe I want other food. Maybe I feel like pancakes today. It takes a moment or two, because not only is it searching for the embeddings, it's then passing the embeddings into an LLM to identify how closely it matches it. It pulls the summary out and then gives you more information. So if we notice here, I'll just open this up so you can see a little bit better. You probably can't read all this text, but it's basically a summary in text of what's going on in the segment. Again, this is based on taking a video, splitting it into pieces, and shoving it through this pipeline and coming out with a result. Now, since I'm in the mood, Eric played a little joke on me a minute ago, and he decided to send me a video where he basically texted me a whole bunch of eggplants. I don't know why. That's going to be hard to see. But the point is that this happens fast. I uploaded this video, and within seconds, it was already embedded, and I was able to search across it. I didn't tell the thing that there was eggplants in it. I didn't even tell it that it had anything to do with any food at all. It found what it was looking for based on just using the vision language model to derive semantic meaning from it. Now, how many of you went up to Snow Basin last night? So we like to do things a different way here. And oftentimes, the way that we do things ends up getting a little silly. Like, for example, we like to have fireworks that are lit. That was fun, right? Watching people ski down a mountain, having a bunch of fireworks lit off, that was a lot of fun. So let's see what we got. Oh, we got some videos of fireworks. By the way, I did have a QR code people could have scanned in the room, but that seemed like a lot of logistics. I didn't want to do it. But then I also notice there's a lot of dancing that happens, and somehow, in the middle of all this happening, people had to take shots. There was a lot of shots taken. Who here got to take a ski shot? Yeah, I took way too many. Now, why did we choose video to show you? Because a lot of you in the room are not processing video. You're not collecting video. You're not trying to derive reasoning from video. Part of the reason is because we wanted to make sure you understood that, look, video is hard. It's easy to get meaning from a text document, right? There's been ways to do that for a long time. Video is so much harder, and it's not just so much harder because it takes a much more sophisticated model to understand it. It's harder because think about all the footage that's collected by a lot of organizations and how many embeddings it would generate, how many database records it would generate, how many petabytes or exabytes worth of storage it would need. It's a massive scale. And to be able to create search on top of video proves that to create search on top of something else is nothing. And so I encourage you to pull down the GitHub repository, look at it for yourself, give us feedback, because we want to help build with you, and we want to understand what you want to do with what we have. And with that, I'll turn it back over to Alon to finish this out.
Thank you, Andy.
I had no more slides.
I needed to go back. One slide. Thank you.
Jeff deleted it.
OK. Last chapter, chapter 3. We have models. We have agents. Let's talk about how models can improve over time. So while RAG is useful for extending a model's knowledge, there's another very popular method called fine-tuning that is much better for many use cases. An analogy could be raising a kid all the way from the day he's born until he's 18 versus taking an intern that already knows English, already has a lot of basics learned, and just giving them 3 months of extra training for a specific domain that you're working on. So we see a lot of good examples out there, or examples like customer support bots. A customer support bot needs to understand the product documentation, it needs to understand the personnel, it needs to understand the jargon. Doing it with RAG usually just yields inferior results. Another example around robotics is learning new tasks. So you could take a VLM and you can feed it with a bunch of examples of how to make pancakes or how to fold the laundry. And that way we can see visual models become mission-focused and can achieve more and more. A very big challenge with robots, specifically in edge devices, is that they're very limited in power, very limited in compute. So for many applications, fine-tuning is really the only way to bring those applications to production. Now, this entire process leads to this interesting feedback loop. We call it the data flywheel. If we record the interactions a robot has with its environment, what it hears, what it sees, what feedback it gets from humans, we can then fine-tune its models daily or even hourly in a fully automated fashion, created a continuously improving system. The implication is constant flow of data from the edge back to the AI factory with frequent updates to software and models. So let's see what we covered. Models, agents, and continuously improving systems. We'd like to partner with each and every one of you on your journey, right? And it doesn't have to just be on the new shiny AI stuff. It could also be the more enterprisey, mundane, and day-to-day things that everyone is still handling. Supporting your existing data systems, existing applications, moving data around. And hopefully we're going to make them more AI-ready and more approachable to the end users, to the developers, and to the agents that are going to accelerate our productivity. On a personal note, we're 10 years into this journey. I can tell you the biggest satisfaction we get is from working with our customers, creating together, learning together. So thank you all for coming.